in 3.2 example 2, what we're looking at is the analysis of a real life situation. So it talks about how a frog is sitting on a rock and he's jumping into a pond. The height of the frog of the surface of the water is defined by the variable h, and then the time since it jumped can be modeled by this function. Now, there's a bit of a typo here. This shouldn't be negative 490 times t times 2. This function should actually be, I'm going to write underneath that the height of the frog as a function of the time since it jumped is equal to negative 490 times t squared plus 150 times t plus 25. But it's very important that as soon as we look at this question, we understand that there's some restrictions on the variables. Because we're defining this as the frog's jump, if the frog hits the water, which is when h is equal to 0, he's no longer jumping. So we know that h must be greater than or equal to 0, and the moment he hits the impact, I guess, is the end of his jump. And we also know that, although it would be cool, the frog can't jump back in time, so t must be greater than or equal to 0. Now, there is no reason that height can't be any real number. We have all sorts of fractional heights, and that goes for time as well. Now, the reason I think this is so important to write is because what it's really telling me is that anywhere that h is 0, I don't have to worry about. So that's quadrants 3 and 4. Anywhere that time is 0, and I'll do that in red, I don't have to worry about, and that's quadrants 1 and 3, which means the only part of this graph that has any relevance to the question is quadrant 1, which is where time is positive and height is positive. So what we're going to do then is we're going to model this function, but your calculator cannot use h and t for variables. So on our calculator, what we are going to type in is y is going to represent the height, and x is going to represent the time. And this is pretty typical that when we use technology, we often, by some quirk of the technology, are required to use a different variable. But we really just have to make sure we remember that y is the height of the object and t is the time of the object. So what we're going to do now is we're going to grab our calculators and we're going to put that function in. So we do that by going to y equals, being really careful with the numbers, we're going to have negative 490x squared plus 150x plus 25. And really crucially, we do not want to use Zoom standard. All right, Zoom standard is going to put 10 in every direction. We know that we don't have to worry about when x is negative. Now, I can make x min 0 because I don't care about it. I like to see those axes. So I'm going to make x min negative 1, and I'm going to make y min negative 1. Now for x max, we are talking about a frog jumping into the water. I doubt that he's going to be in the air for more than 5 seconds. For y max, it's a guess. Students don't like that. I get that. But you really just have to kind of ballpark and see what happens. One of the advantages of some of our kind of theory is we know this graph opens down because the a is negative, and I know that my constant is 25. So when time is 0, the frog is 25 centimeters above the water. What I often recommend students is maybe just multiply your y-intercept by 10, and we'll see how it looks. So there's my graph, and certainly this does look like if you throw an object, this is what it would look like from the side, but we don't really see a lot, and I'd rather have my scale kind of represent exactly what that frog is doing. So it looks like my x max and my y max are far too large, so I'm going to change those. And this is why we like using technology, because it's easy to change. I'm going to make x max 2 because it looks like the second tick more than contains my graph. For y max, 250 was a little much. I think I'm going to go down to 50. Now when I graph it again in a relatively short time, it gives me a bit of a better curve to deal with that frog's jump. I don't like how much empty space there is, and you don't need to change it, but I like it to look a little bit neater than that, so I'm going to make x max 1. And then it looks a little more like an object falling, or I guess jumping through the air. All right, with this graph, we can now answer these questions. And we didn't need the graph for all of them, right? Part A, we already did. That's on our calculator. And I'll just put on calculator there. We have that. We're going to refer back to it again and again. For B, it says, what is the y-intercept? What does it represent in this situation? I'd like to write that the y-intercept is the height at 0. So that's negative 490 times 0 squared plus 150 times 0 plus 25. So the height at time 0 is 25, and what this basically represents is the starting height, or because the frog is jumping from a rock, it's the height of the rock above the water. And it is very, very important that you read these questions carefully because they could define that height as maybe from the bottom of the pond, but it does tell us that height is above the surface of the water. So that's not the case for this question. All right, C wants us to find, and I'm going to try to get the questions where we can still see them here. So C wants us to find the maximum height, and when does it reach that height? Now, I'm going to draw just a quick little sketch of what this frog's jump looked like based on my calculator, and roughly it looks like this. So the maximum height is going to be this point right here, and it's really important that that has a very specific terminology when it comes to parabolas, which is the vertex. And moreover, I'd like to identify that that vertex is a maximum. And that makes sense. Anything that jumps is going to have a maximum height because gravity is accelerating it downwards. Now, in order to find that max height, if you carry on in math, you will eventually learn how to do this algebraically. It requires something called the derivative. We're not going to do that. So if we ask you to find where that vertex is without completing the square, which is 3.3, so we're not doing it today, what you have to do is you have to go to your graph. You have to have it, on the graph as we look at it. And then you go to second trace, and you'll see a bunch of different options here. One of them should jump out, which is the maximum. So what this maximum option does is lets us find the maximum of graphs. Some graphs have more than one maximum. So what we have to do is we have to make sure that our left bound and right bound contain the maximum that we're looking for. So when x is equal to 0, I'm pretty clearly to the left of that vertex, but then I need to hit the right cursor until I'm to the right of the vertex. Now, there's no golden rule that you have to be 4 ticks to the right or anything like that. You just have to be clearly to the right of the vertex. The guess doesn't matter. The guess is only useful if there's multiple vertices in the same bounds. So I'm just going to hit enter again. And my calculator tells me that this maximum occurs at 0.153 and then 36.47. And I am going to cheat a little bit because I never remember these numbers when I do it on my calculator. So I am just going to grab them with the screen cap. And then what we know is that because our maximum is, and this is really important, we have to think about what these variables are representing. The x is representing the time, and the y is representing the height. So what this means, and I'm just going to go to the nearest thousandth here, at 0.153 seconds after launch, the frog is launching off of the rock, the frog's max height, an apostrophe, I don't know, we'll just go frogs, max height, not an English teacher, is, and then we can read that y value. So that's going to be 36.47, that's going to round up. So it's 36.480. And if we look back in the question, and maybe I'll scroll up so we can see it, it tells me that the height is in centimeters. Really important to read your units carefully because a frog jumping 36 meters is a lot more impressive than a frog jumping 36 centimeters. So read the questions carefully and make sure you know what each variable is representing. All right, a few more here. D says, when does the frog hit the surface of the water? Now, keep in mind that when y is 0, it's this right here, this wavy blue line, that's when the frog is basically at the height of the water, or the water top. So he's going to hit the water. Remember, the t can't be negative, so it's going to be our positive x-intercept. In order to find that on our calculator, again, we have to have the graph in. You can't analyze a graph without having it graphed. We're going to go to second trace, and then 0 option. It's kind of annoying that they labeled it 0, but it's basically determining when the value of the function is 0, which is its x-intercepts. So I'm going to go to my 0, and we get a very familiar prompt, which is left bound. So making sure that we identify we're finding this x-intercept, that's definitely to the left of it. I'm going to hit my cursor until I go to the right. Now, a little trick is that as you move your cursor, it tells you where it is. So I am not to the right of the x-intercept until my y value is negative. So as I cursor slowly to the right, we see that as soon as I'm to the right of the x-intercept, my y is a negative number. So that's right bound. Again, guess doesn't matter. And I get that 0 is at 0. I'm going to do this again because otherwise I'll forget. So 0.42591 3, blah, 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 blah. But the frog hits the surface of the water. And again, I'm going to go to the nearest thousandth. In general, I think that's good enough. So it hits the water 0.426 seconds after, and I'll put launch again here, after it jumps. They really mean the same thing. I'm not too worried about the language that you use there. But it is a really important, skill to cultivate, to be able to look at a graph and find the x-intercept using our calculator. Oh, there's a couple more. What are the domain and range? And then how high is the frog 0.25 seconds after it jumps? Let's do domain and range first because they're not too bad. Now, the previous quadratics we've looked at, our domain has been all real numbers. But this has a real world context. And I said above that, t can't be negative. The frog can't jump back in time. So when we talk about the time, my t variable, the time must be greater than or equal to 0, but it must be less than or equal to 0.426. Because as soon as that frog hits the water, it's no longer jumping, it's swimming. And that would have to be modeled by a different function. Not sure why I wrote 0 twice there. Sorry about that. That should be the variable we're talking about, t. And then, because time is continuous, it can be any real number in between those restrictions. For height, again, we know that it must be greater than or equal to 0. So height must be greater than or equal to 0, otherwise the frog isn't jumping, but the frog has a maximum height. So the height must be less than or equal to 36.480, and again, height is an element of the real. Right, domain and range can be tricky when you're using real situations. A really, really common restriction in real situations is that time must be greater than or equal to 0. We're not going to deal with any kind of, backwards time travel in our math courses. All right, the last question there, and I remember it, which is convenient. F wants us to know, and I'm going to write this in function notation, it wants us to know the height, or determine the height at a time of 0.25 seconds. Now, there is nothing wrong with actually plugging that in. So I could say that the height of this frog at 0.25 is equal to negative 490 times 0.25 squared plus 150 times 0.25 plus 25. I could do that. There's nothing wrong with that. But our calculator is designed to really be able to do stuff like that very, very quickly. And the way that we do it, you might guess, based on what we've done previously in this question, that we need our graph up. Then I go to second trace, which is the calculate menu, and I am looking to calculate the value. So when I go to option number 1, it has this x with a blanking. I need to tell it what x I want. So if I put in 0.25, it tells me that when x is equal to 0.25, y is equal to 31.875. That is the coordinate on the kind of trajectory of the frog. And this lets me identify really quickly that h at 0.25, that's my time value, is equal to 31.875. And then I'm just going to write a little sentence here. At 0.25 seconds after launch, the frog is 31.875 centimeters above the water. Now, admittedly, using this level of math on the trajectory of a frog, probably not that useful, but autopilot in planes, any type of satellite motion where we want to get it into the right space, the right orbit, all of that involves this type of mathematical analysis, although they might not be strictly quadratics.